So today I will be giving a review on the internal rapid rotation in stars and how it affects their structure and their pulsations. And of course, given the amount of time, I will have to make some choices. I won't be able to describe everything because it's a vast topic, and I'll give my own, perhaps biased, point of view on this topic. All right? So, first of all, in terms of introduction, I'd like to talk about massive stars. Massive stars are very important for several domains in astrophysics. They dominate the chemical evolution of galaxies through their winds, their supernovas. And here on the right, you have the aftermath of a supernova. And then they're likely to be the progenitors of gamma ray bursts. Intermediate mass stars are different than massive stars in the sense that they do not explode in a supernova. But in spite of that, they share many of the same physical phenomena. However, they're much more numerous than massive stars. So from an observational point of view, it's more interesting to study them. And then some of them have very rich pulsational spectra. And this is illustrated on the right. So here you've got a frequency spectrum of a delta Scuti observed by CoRoT. And you can see that even after subtracting 1,000 pulsation frequencies, you still have a residual here. What makes these stars different is that a significant proportion of them are rapid rotators. And you can see this in this histogram, which shows the projected equatorial velocity as a function of the spectral type. And you can see that for types earlier than F0, you have quite rapid rotations, whereas for solar type stars, you're really a lot slower. And so if you want to understand these stars, you have to understand the effects of rotation and how it impacts their structure and evolution, and also their pulsations. So in today's talk, I'm going to talk about the impact of rotation on stellar structure and evolution. Then I will focus on how rotation modifies pulsation modes. And then afterwards, I'll describe the latest efforts in trying to interpret pulsations in these stars. Okay. So one of the first and most obvious effects of rotation is centrifugal deformation. So this distorts the shape of the star by making the equator bulge. And this has been confirmed with recent interferometric observations, which show that some stars can be highly distorted, such as Achernar, which you can see in these two interferometric reconstructions. And this means that to model these stars properly, you can only do it with a two-dimensional approach. A second effect of rotation is gravity darkening. Gravity darkening causes the poles to be hotter than the equator. And so this means that the position of these stars in an HR diagram will depend on their inclination. So this needs to be taken into account when you study these stars. And gravity darkening is confirmed also by interferometry, as you can see in these three different stars. And it can even be useful for determining the inclination of the star. So for example, Vega is a nearly prolong, whereas Alpha Leo seems to be more equatoron. Now there are different ways to model gravity darkening. You have the von Siepel approach, which basically says that the radiative flux is proportional to the effect of gravity. Furthermore, since the flux is proportional to the effective temperature to the fourth power, then you deduce a power law between the effective temperature and the effective gravity. And this power law will have a 0.25 exponent. But then there have been later studies which investigate what happens if you have an outer convective envelope. And these studies point towards a different power law. Then more recently, Espinosa, Lara, and Riotor came up with a different law, which is based on the assumption that the radiative flux is parallel to the effective gravity. And then they just simply worked out the consequence of saying that the divergence of the flux is free because you're not generating energy in the outer portion of the star. And so when they worked this model out analytically with the Roche model, they come up with a slightly more sophisticated law. And so here in this diagram, it shows how the exponent changes as a function of the stellar flattening. So this would be a non-rotating star, and then you go to more rapid rotations to the right. And so the analytical model is this continuous line, whereas full 2D calculations would be given by the symbols. And then finally, these boxes would be constraints deduced from interferometry. So you can see that it agrees quite well with most stars. Now, a more complicated effect of rotation is called Baroclinic effects. And according to this, lines of constant pressure, temperature, and density do not coincide in rotating stars. And so as a result, this will generate torque within the star, which will provoke meridional circulation, as you can see on the right. And then this will carry angular momentum and set up a differential rotation profile, as illustrated on the left. Now, this will have a long-term impact on the star because it will enhance transport processes, which will effectively increase the core of these stars, or the amount of available material for nuclear combustion, and so prolong their lifetime on the main sequence. And then, of course, it will modify their chemical yields. And Anna Palacios has already talked about this a few days ago. Now, using this sort of baroclinic effects, there have been a whole bunch of models which model how these stars change as a function of time. So this is an HR diagram showing theoretical tracks. And so the dotted black lines show the evolution tracks of non-rotating stars. And the continuous red lines shows what happens if you have an initial equatorial velocity of 300 or even 400 kilometers per second. And so you can see that the evolution of these stars is modified by the enhanced transport processes. And so these models have had quite a bit of success in explaining the chemical enrichments of massive stars, so O, B, and A stars, and has also helped explain the number ratio between blue and red supergiants in one of the Magellanic Clouds. However, there have also been some difficulties. There's what's known as the Hunter diagram, which shows the nitrogen enrichments as a function of the projected equatorial velocity. And so according to the rotating models, you should have stars which rotate rapidly should be more nitrogen enriched than stars which are non-rotating, because rotation helps to bring nitrogen to the surface. And so that means that the models tend to fall along here, as is illustrated by this density scale. However, the observations show that there's a significant number of slowly rotating stars which are enriched in nitrogen. And then there's also a significant number of stars which are rotating rapidly but are not enriched in nitrogen. So this is a challenge for theoretical models. And then, as we've heard also a couple of days ago, there's also a significant mismatch on the rotation rate of the cores of red giants. One can also look at the impact of rotation on convection zones. And so in an article in 2007, Espinosa, Lara, and Riotel showed that you could have a negative Brunt-Weissler frequency, which is confined to an equatorial belt, as is illustrated in this figure right here. A year later, Meder also studied the impact of rotation on convection and found that rotation does favor convection, especially at the equators, or at the equator, I mean. However, one difficulty is to know how to model convection in a two-dimensional setting. Is there some sort of equivalent to the one-dimensional mixing length theory? And so this is an open question, but perhaps the answer might come from a new project called the Chorus Code, which models convection, well, for the moment in spherical stars, but will be able to handle oblate stars. And so here's a benchmark which shows a comparison between Chorus calculations and calculations from the Ash code. So in summary, rotation causes many new phenomena in stars, which affects transport processes within them, mixing, and then on the long term, their evolution. And although there's been significant progress over the past few years, there are still large uncertainties. And so to be able to make further progress, we need observational constraints on their internal structure. And the best way to do this, as you know, is through astroseismology. So in the next part, I'm going to talk about how stellar pulsations are affected by rotation from a theoretical point of view. And then after that, I'll talk about some of the latest observational efforts in interpreting these pulsations. So a few days ago, Don Kurtz talked about one of the first effects of rotation. So in this diagram, you have frequency pulsations as a function of the rotation rate. And so this is for a given L and N value. And at zero rotation rate, modes with different azimuthal orders will have the same frequency, and you can see this by the convergence of these different lines. But then as you increase the rotation rates, you'll get distinct frequencies, which are separated by what is known as the rotational splitting. And so at low rotation rates, this will be a uniform splitting between the different modes, provided that the rotation profile doesn't depend on latitude. But then as you increase the rotation rate, then you start having to include higher order terms of the rotation on the frequencies. And then afterwards, as you continue, then you can no longer do it using an expansion series. You have to actually do full two-dimensional calculations to correctly calculate the pulsation frequencies. All right. So now I'll focus on the low frequency modes. So these would be known as gravito-inertial modes in rotating stars. And the restoring force for these modes would be a combination of buoyancy and the Coriolis force. So these modes are highly sensitive to the Coriolis force, and this can be quantified by the following ratio, which is basically the ratio of the pulsation time over the Coriolis characteristic time. And the type of stars that will be affected the most by this will be gamma Dor stars, which are right here, SPB stars, and then BE stars, which are somewhere around here. Now there's been quite a lot of different articles on gravito-inertial modes, and also in particular on inertial modes and singular modes. And here's just a list of some of the references, including a poster that's in this conference. However, in what follows, I will focus more on more classical modes, which become G modes in the non-rotating limits. Okay, so gravity modes in a non-rotating star are uniformly spaced in periods. So you calculate the pulsation period of successive modes, and you'll find that this period spacing is uniform, provided you're dealing with a given L value. Now, when you include rotation, then this is no longer true. The period spacing will start depending on the azimuthal order and also the parameter eta, which is just simply the ratio between the rotation rate and the pulsation frequency. And so you can see this in this diagram, which shows the period spacing as a function of this parameter eta. And you can see various numerical calculations represented by these crosses, and then how they kind of all fall on the same curve. Now, this is already established using the traditional approximation, and there's been a number of studies on this, but the latest studies with Jérôme Barou show that this continues to be true even in the full two-dimensional case with stellar deformation, except perhaps here where the deformation does play a bit of a role. Now I would like to talk about the geometry of these modes. And so when dealing with the geometry, it's very important to distinguish between subinertial modes and superinertial modes. So subinertial modes have their frequency below twice the rotation rate, whereas superinertial modes have their frequency above twice the rotation rate. So subinertial modes will have their pulsations confined between critical surfaces. which are defined as the transition from a hyperbolic to an elliptic differential equation. And you can find analytical expressions in these articles. And so you can see that this mode, when it, at sufficient rotation rates, goes into the subinertial regime, and it is confined in the equatorial region. Then you have superinertial modes, which really look quite a bit like their non-rotating counterparts. And then you have another very special type of mode called rosette modes, which take on a very different geometrical shape, which looks like a rosette. And we'll hear more about these modes in Masao's talk, which is right after mine. So now I'm going to talk about acoustic modes. So for acoustic modes, the restoring force is pressure. Now, since these modes are located towards the outer portion of the star, they're strongly affected by the centrifugal force. And you can characterize this by the ratio between the stellar deformation, represented by epsilon here, and the characteristic wavelength of the pulsation mode, represented by lambda. And then if you express this in terms of the rotation rate and the pulsation frequency, then it will be proportional to this quantity right here. The stars which are the most affected by rapid rotation, which are acoustic pulsators, would be delta Scuti stars, which are shown right here, and beta Cephei stars. So when you go to rapid rotation rates, well, you'll have different classes of modes, as was shown using ray dynamics by Lignières and Georgiou. And so these different classes of modes have a separate characteristic geometry, as illustrated in these meridional cross-sections of the pressure fluctuations. And they also have their separate frequency organization. And then this was also shown to be true in more realistic models, because it was first established in polytropic models. And so in this next slide, you can see how the frequencies of these different classes of modes behave. So the island modes, and there's also another class called the 6-period island modes, and the whispering gallery modes follow regular asymptotic patterns, as illustrated here, whereas the chaotic modes follow a statistical distribution. Among these different classes, the most important, I would say, are the island modes, because they are the most visible of the regular modes. They are the rotating counterparts to low-degree modes. And so when you go to rapid rotation rates, the nodes are shifted around, and so you have to introduce new quantum numbers to describe these modes. So you have n tilde, which is the number of pseudo-radial nodes, and then L tilde, which will be the number of nodes in the latitudinal direction. And this is illustrated in this diagram right here. But you can still relate these quantum numbers to the more classical spherical quantum numbers through what could be described as node conservation. And so here are the formulas which relate the two. Now, introducing these new quantum numbers is quite useful, because it is easier to describe the frequencies of these modes in terms of these new quantum numbers. So using empirical fits, you can describe the frequency using this formula, which is actually a simplified version of the formula given in this article. And the different quantities which intervene in this equation can be described using asymptotic analysis. So this delta n tilde would simply be the travel time along a ray path, which would go right here. All right. The delta L tilde takes on a more complicated expression, which is given in these two articles. Now, coming back to the delta n tilde, in fact, it is related to the large frequency separation from the non-rotating case. It's just simply 1/2 of it. But furthermore, what you can do is see how the large frequency separation behaves as a function of the rotation rate. And you can normalize it by different quantities. And it turns out that, in fact, this scales with the square root of the mean density. And when I say mean density, I am taking into account the fact that the star has been flattened, so I'm calculating the true volume of the star. And so this is useful because it can be used to constrain the mean density of these stars if we can somehow measure this quantity. Now I just want to also talk about mixed modes. So you have a series of 3 plots which shows the frequency as a function of the dominant L value in the harmonic expansion of these modes. And so you can see above here you have acoustic modes, and below you have gravito-inertial modes. And as you increase the rotation rates, these gravito-inertial modes come up higher into the acoustic domain. And this is because gravito-inertial modes do not scale with the mean density, but more with the ratio m over the polar radius cubed, because these modes are more confined to the interior of the star, and so they're less affected by the centrifugal deformation. Whereas the acoustic modes scale more with the square root of the mean density. So because of this increased overlap, you'll have interactions between acoustic modes and gravito-inertial modes. And you have to remember that in the rotating case, you don't have to have the same degree to have avoided crossings between these modes. So they'll start mixing up and taking on a mixed character. Afterwards, one can also go to slower rotation rates and study more evolved stars, which naturally do have mixed modes. And in this case, what happens is that rotation can affect individual members of a multiplet so that they have a different P or G characteristic. And so this will lead to uneven frequency splittings, or rotational splittings, as was shown in an article by Rita recently. So now I would like to talk about current efforts in trying to interpret these stars. So in Asteroseismology, you can distinguish between 2 approaches. You can take on an average or a global approach, where you try to find general characteristics of the observed spectrum rather than focusing on specific modes. And then afterwards, you can have a more detailed or boutique approach, which relies on actually identifying individual modes. So in terms of global astroseismology, there's been quite a bit of work in the low frequency domain. And so here you've got a BE star, which is observed by most. And you'll see that there are different clumps of modes, as illustrated in this frequency spectrum. And then above you have models to try to reproduce this. Now what is actually happening is that the frequencies of these modes in the co-rotating frame are quite small. In fact, quite a bit smaller than the rotation rate. So then if you have modes with different azimuthal orders, it'll separate these modes into separate clumps. And so the distance between these clumps approximately corresponds to the rotation rate. And of course, then you can use more sophisticated techniques using, for example, non-adiabatic calculations to see which clumps are more likely to be excited, as was done, for example, in articles by Li and co-authors. And so here's various references on this star and similar stars. However, there's also been a recent study by Thierry Simon, who investigated these rotation rates deduced by seismology, and that's shown in the pink, with the pink bars right here. And then he and co-authors tried to also determine the rotation rate using other independent techniques, and that's shown by the green bars. And what they've shown is that there are discrepancies. So there's a bit of an open question as to what is causing these discrepancies between the two. In the high frequency domain, you can study the statistical distribution of the modes using, for example, Fourier transforms, such as what is done here, or also autocorrelation functions or histograms of frequency differences. And in some cases, you can find recurrent spacings, such as illustrated right here. And these spacings are useful because they could be the large frequency separation. And as I've shown you earlier, this can be used to constrain the mean density. And so Antonio and co-authors have been working on this in Delta Scuti stars, and they found the spacing in a Delta Scuti star here. And there's been a number of other studies also looking for recurrent patterns in observed stars. And so Antonio has a poster on that. And on the theoretical end, we've also worked on seeing if you can expect to find such signatures. And so this is shown in the autocorrelation function of frequency spectra, where we've selected modes according to their visibilities. Now I'd like to talk about detailed Asteroseismology if there's time. I'd like to start by asking a simple question: why is it so difficult? And I think the answer to this question is nicely illustrated in this diagram. So these thick circles correspond to the observed pulsation frequencies, and then below, this variety of symbols corresponds to theoretical frequencies. And as you can see, identifying the modes in such a context is not straightforward. So how can you identify the modes? Well, you can still try to look for frequency patterns. I'll describe that in the next slide. And then you can also use other observational techniques to try to constrain the identification. So there's typically multicolor photometry, which relies on amplitude ratios and phase differences. And the advantage of this is that by calculating ratios, you factor out the intrinsic amplitude, which we don't know how to calculate anyway. And then you can also use spectroscopy and look for line profile variations. And this gives you more detailed information. But of course, these methods have been typically applied to slow rotating stars, and they need to be adapted to more rapidly rotating stars. So first of all, talking about frequency patterns, once you've identified the large frequency separation, you can then construct echelle diagrams. So this is illustrated in this plot by Antonio and co-authors, and you can see that there are ridges. So this is one step towards identifying the modes, but I think there's still a lot more work that needs to be done. And a few days ago, we've also heard in Tim Bedding's talk about progress in constructing echelle diagrams for G-mode pulsators. Now for multicolor mode identification, you can look at amplitude ratios. One big difference with the non-rotating case is that modes with different azimuthal orders will have different amplitude ratios. However, if you fix the value of the harmonic degree and the azimuthal order, then they will have similar amplitude ratios. And using this, you can try to constrain the identification. So this is what is proposed in this article. You basically take a whole spectrum of modes, and then you group them together according to modes with similar amplitude ratios. And this will lead to modes which have similar L and M values. Then, for spectroscopic signatures, you can also look at observations here. So you can see how you have bumps moving within this absorption ray. And then you can compare this to theoretical calculations using tools such as FEMIES. And this can help to constrain the identification of these modes. However, for these methods to work properly, you really need to be able to calculate the variations in an effective temperature. And this can only be done accurately using non-adiabatic calculations. And furthermore, another advantage of non-adiabatic calculations is that you know which modes are excited, so that can also be used as a constraint. Now, there have been various studies, especially by Yumin Li and also co-authors, who have looked at how non-adiabatic effects play in the pulsations of rapidly rotating stars. And they've worked on models which are based on Chandrasekhar expansions. And currently I'm working on applying the same sort of methodology but using Esther models. And the advantage of these models is that they solve the energy equation in a self-consistent way. So here are just a few very preliminary results. So this shows an acoustic mode, the pressure fluctuations. This shows the regions of excitation and damping, but of course it's a bit hard to see because it's very close to the surface. So this shows the radial coordinate here has been replaced by the log of the temperature. And so then you can see how modes are affected by rotation. So this would be a low frequency acoustic mode, multiplets in fact, and the work integral. So these modes are excited. And as you increase the rotation rate, you can see that the retrograde modes become damped progressively, and then afterwards, even finally, the prograde modes are damped. So now to conclude, I would like to say that rotation does play a major role in massive and intermediate mass stars. And if we want to understand these stars, we have to understand the effects of rotation. And it is important to understand these stars because it affects many domains in astrophysics. And So there's also been a lot of progress in interpreting their pulsation spectra. But I'd say there's more work that is needed, especially with the current exquisite data from various space missions and also future space missions. So thank you for your attention.
Thank you, Daniel. So is there any questions?
Hi, thank you. That was a wonderful review. On P modes, you said that the large spacing is still proportional to square root density, provided you calculate the true volume of the star. So I assume as the star spins, it gets bigger and the density goes down.
Exactly.
So my question is there a simple formula for that? And for stars that are only rotating moderately, should we be worrying about it? Because delta nu is one of our key parameters that we use for all stars.
Okay. Say for moderate rotations, it probably won't have a very strong effect because the deformation goes as omega squared. But then if you want to go to rapid rotations, one way you can do it is using Roche models. It won't give you an analytical formula, but it's fairly straightforward to program, and you can get a pretty accurate estimate. And I have investigated the difference in shape between some of the models I use and Roche models, and it's very, very similar. So I think that's a simple way of going forward.
Thank you.
I'd like to echo Tim. Thank you for that very thorough review, Daniel. Simple question, but I think a hard answer. Peter Papert showed us a very slowly rotating B star where the splittings were not equal. How can that happen?
That's a very good question. Yeah, I think I don't really know, but. Okay.
Yes, I would like to ask, when you showed that you can separate the horizontal quantum numbers, L and M, using color photometry, have you an idea of which way you could separate the radial quantum numbers?
Well, I think you'd have to start doing comparisons with models. So first of all, you'd have to quantify the L and M values, and then if you can get a sequence of frequencies, then I think you might have more of an idea on the radial, but it will be model dependent.
Mm-hmm.
I noticed you considered the rotation rate of 0.8 omega Kepler. So my general question is, what's the maximum rotation rate of this kind of massive star? Is it by mass shedding, basically when the equatorial rotation rate equal to Kepler value, or are there any dynamical instabilities that set in due to some modes? As in the case in classical work of uniform ellipsoid, uniform Maclaurin spheroid.
Okay, I'm not sure I know which star you're talking about.
Well, I'm just in general, I guess. What's the maximum rotation rate? That's mass shedding or dynamical instability?
There's been various studies, especially on BE stars, which suggest they're fairly close to the critical rotation rate, although there's still some open questions because some of them seem a bit too low to be able to eject matter. But I think people look towards pulsation mechanism and maybe even interactions between various pulsation modes to try to eject matter as the star is rotating. And so even though it's below the critical rotation rate, it's still able to eject matter. The critical rotation rate means that the effective gravity at the equator is 0. So the centrifugal force exactly balances the gravity.
Thank you again, Daniel.